yes, check out the recording. All right. So where we left off last week, if you remember, we're doing the multiplication rule for independence events, and we started doing the multiplication rule for dependent events. So dependent event just means that the probability of one event changes the probability of the second event occurring. So what you do in the first event will influence the probability of the second event occurring. So the problem that we did last week was this one about a jar and us randomly selecting 2 marbles from the jar. So that's where we ended last week. So we're going to continue on with that idea with the next problem. So the next problem is 2 card will be randomly selected without replacement from a standard 52 card deck. So one thing you kind of have to understand is the word without replacement. So without replacement just means once you select that item, you can reselect that item again. So once you choose that one item, you're not gonna be able to select that car in this case scenario again. So once you select that car, you're not gonna be able to reselect that car again. So let's go ahead and do part A. So part A says, are the event the first card is heart and the second card is spade? Are these independent events? So in this case scenario, we're gonna say no, since one affect the other. Because if you randomly select one card, it's gonna change the probability of the next card being selected because now we have one less card to draw from. So that way, for this case scenario, we're gonna say they're not independent. So we're gonna say they're actually dependent. All right. Any question in regard to why are they dependent? Cool. If you actually look at these 2 events, these 2 events will be considered mutually exclusive because pretty much you're either gonna get over here. Because you're either gonna get a heart or you're gonna get a spade, but it's impossible to get a heart and a spade. Okay. Right. So let's do B. So it says find the probability the first card is a heart and the second card is a spade. All right, so hopefully you know about a card of deck. If you don't, we'll essentially help you out. So in a card deck, there should always be 52 cards. So you always start out with 52 cards. So hearts, you actually have 4 hearts that are red. You also have 4 spades, but this is actually black. You also have 4 clubs. Oh, that's pretty ugly. And that's black too. And then finally you have 4 diamonds. And the diamonds are red. So for this one, which number should I put on top right here if we want to find the probability of getting a heart?
4 out of 52.
Cool. So we put 4 out of 52. All right. Everybody good with 4 out of 52?
Yeah.
Cool.
Yeah.
So let's kind of imagine that the first card that we pick. Oh, wait. Actually, this is all wrong. It should be 13. So sorry, there's 13 hearts. Well, red heart. There's 13 spade, 13 clover, and there's 13 diamond. So which number should I put on top?
No wasting.
13.
Yeah, cool.
Save it for you. You're gonna eat it.
So let's imagine that we got a heart, and let's say we got a king of heart. So that's the first card that we draw. So we get a king of heart. So how many cards do we have left?
51.
Yeah, 51. Cool. So you see how this first draw affected the second draw? Because
Yeah.
now instead of it being 52, now it's 51. So that way this is the dependent, because the first draw is going to influence the probability of the second draw, because now we only have one less object, or in this case, one less card to choose from. All right. So when we pick this heart, did that affect how many spades we have?
No.
No. So what's the probability that we get a, well, how many spades do we have to choose from?
Oh, we have 13. No,
Yeah, you have 13. So
How is it?
all right, everybody good? How we got 13 divided by 52 times 13 divided by 51?
Yeah.
All right, so we're gonna go ahead and do that. So we're gonna say 13 divided by 52 multiply by 13 divided by 51. And you got,
Are you going with December tomorrow?
10637.
yeah. So we're gonna say 6.4%, because I'm running out of space right there. All right, but that's it for B.
I have a question.
Yeah, what's up?
So like while I was doing the homework, sometimes I would get a little confused on when to multiply and when to add. So this one, because it says without replacement, that's why we're multiplying.
Not because it said without replacement, because we're doing multiple selection. Okay, if you look right here, we're selecting 2 cars. That's why we're multiplying.
Okay.
Yeah. All right, so let's do part C. So for part C, it says, are the event the first card is a 10 and the second card is a king? Are those independent? So should we say they're independent, or should we say they're dependent? If you don't want to talk, you can either put it in the chat, or if you just want to shout it out, just shout it out.
Dependent.
Cool. Yeah, so this one should be dependent. Cool. So they're both dependent, and the reason they're dependent because your action, the first one, is going to influence the action of the second one, or it should influence the probability of the second one, because now we're going to have one less card to choose from. All right. So let's do this. So one thing you have to kind of know, so for aces, they're 4 card. There's 2, they're 4 card. They're 3, they're 4 card. For 4, they're 4 card. All the way to king, they're 4 of each. So for this one, it says, what's the probability that the first card is a 10? So we're going to do a 10. Cool. So for this one, how many total cards do we have?
52.
52. So we still put 52 in the bottom. How many of those 52 cards are 10s?
4.
Cool. All right. And that's it for that first one. Now we're going to do a king. So since we're doing this without replacement, that means once I select a card, pretty much I'm going to have one less card to choose from, because we're saying it's without replacement. So once you pick that card, you can't re-put that card into the deck of cards. So now instead of 52, this should be 51. All right. Everybody go, why that's a 51?
Yeah.
Cool. All right. So say the first card that we select is a 10, and we'll say this is a 10 of spade. Did that change the fact about how many kings we should have?
Nope.
Nope. So how many kings do I have?
Well, now you have 3.
Well, why would I have 3?
Didn't you pick one?
I did pick one, but I picked a 10 of spade.
I said it's for later.
Oh, my fault. You still got 4.
You still have 4.
King was picked earlier. That's probably it. In the first question.
Yeah.
Oh yeah, for the first question. Everybody get how we got 4 divided by 52 times 4 divided by 51?
Wait, how come there's 4 kings?
So that is the deck of card. The deck of card, you always have 4 of each number. So you have 4 aces, 4 2, 4 3, and you also have 4 kings, 4 queens, 4 jacks, and so on and so forth. So there is 4 of each.
Okay, so so there's only 13 of like the cards.
Yeah,
Wait.
so of these suits, there's 13 of each. But if we're looking at individual numbers, there's 4 of each.
Okay. And okay. So first card is a 10. Okay, because I thought you were doing 10 divided by 4 over 52, but then I was like, oh, the first card is 10. So
No, you're saying the first card is 10.
okay.
All right. So if you look at that, we get 0.6%. All right. And that's it for that one. Any question for that problem? All right, so we're gonna do this last problem, then we're gonna move on. So for this one, I wanna get that the first card is an ace, and I want the second card to be an ace. So essentially we want pocket aces. So we want the first one to be an ace. We want the second one to be an ace. I want you to see how this is different. Because we're gonna have multiple selection of the same card. All right. So for this one, since you start with 52 card, you still put 52 right here. All right. Of the 52 card, how many are an ace?
4.
Yeah, 4. So in order for this to be true, we're gonna assume the first card that we get was an ace. So we're gonna say we get an ace, and we're gonna say it's an ace of heart. So how many total cards now do we have to choose from?
51.
1.
Yeah, cool, 51. Of the 51 cards, how many ace are left?
3.
3.
3. Cool. Because you always, in this case, we're always assuming the first card is any sort of ace. So if we pick an ace on the first time, that means we have one less ace to choose from.
Mm-hmm.
So everybody got how we got 4 divided by 52 times 3 divided by 51.
Yeah.
Sweet.
So, but like, we don't really know if they're gonna pick an ace, but I guess we're just assuming that they do.
Well, yeah, because the thing is, if we want to get pocket aces, or we want both of them to be aces, you have to assume that the first card they get is an ace. Because if they get the first card is like a king, then that's not 2 aces. So in order for this to work, you have to assume the first card you got an ace, because we want both of the cards to be aces.
Okay.
Okay. So we'll do 4 divided by 52 times 3 divided by 51. Cool. And you get pretty much 0.5%. All right. Any question for that last example?
Mm-mm.
All right, so let's scroll on down. Okay, so up next we're gonna get into is called the counting technique. So the counting technique is telling us how many different sequences or combinations do we have. So it's telling us like if we're rearranging the order of something, it's telling us how many ways can we rearrange it. So there are multiple, well, we're gonna learn about 3 different ones, and these 3 different ones kind of depend on what type of technique or how we're selecting them. So the first one, we're gonna use this multiplication rule. So for this multiplication rule, the P, Q, and R is telling us how many options do we have to pick from. So let's kind of go to something that we already know. So let's say we're flipping a coin. So let's say we do 3 flip of a coin. So when we flip a coin 3 times, how many total outcomes are possible?
6.
Let's try that again.
9,
Let's go one down.
8.
Yeah, it should be 8 outcomes.
Okay, 3 times 2, but wait.
But if you remember, we had heads, heads, heads. We have heads, heads, tail. We have heads, tail, heads. We have tails, heads, heads. You have tail, tail, heads. You have tail, heads, tail. You have heads, tail, tail. And you have tail, tail, tail. So those are the total amount of outcomes that you have. But the thing is, you can use the counting or the multiplication rule in order to figure out how many different outcomes you have. So let's do this. So we have the first flip. You have the second flip. And lastly, you have the third flip. So when I flip the coin the first time around, how many outcomes is possible when I flip the coin the first time? Like, what are the outcomes that the coin could land on?
Either heads or tails.
I heard you told right. So it's
Yeah.
2.
So 2, perfect. What about when I flip the coin the second time around? How many outcomes are possible?
2,
2. And the third time?
2.
Cool. So what the multiplication rule in this case scenario says, if I know the outcome each individual event, I can just multiply them and it will give me how many total outcomes are possible. So if I do 2 times 2 times 2, what do I get?
8.
Cool. And that's the 8 that we got over here.
Oh, okay.
So that's what the multiplication rule is doing. Is just saying if I know the individual option for each event, all I have to do is multiply those individual options. And it will give me how many total sequences or outcome are possible for that. So let's do some more example of that. I need space. All right, so let's do this one. So let's say you're going to a local pizzeria and it's offering 2 pizza, supreme or vegetarian, 3 sides, chip, salad, or coleslaw, and 4 drinks, juice, Coke, ginger beer, or water. For dinner, I decided to have 1 pizza, 1 side, 1 drink. How many possible meals do I have to choose from? So for this one, we could choose a pizza.
Más tarde, Luis.
We
¿Vas a
could
pintar?
choose a side, and we could choose a drink. So for the pizza, how many options can I choose for the pizza?
You got 2.
You got 2, so we'll put 2. Perfect. What about for sides? How many sides can I choose?
3.
3, so you put 3. And lastly, for the drinks, how many drinks can I choose from?
4.
Oh,
4. So if I multiply all of these out,
24.
Yeah.
cool, 24.
That's a lot.
Cool. So it's saying we have 24 different combination or 24 different like sequences that we could choose from for this meal. So it could say like we could choose the vegetarian pizza, and then we could choose chips, and lastly we could choose a juice. And this is one outcome. So what the 24 represent, it's telling us we have 24 of these outcomes. So it could say we could choose a vegetarian pizza, we could choose chip, and then we could choose a Coke. Or we could do a vegetarian pizza, we could choose chip, but now we choose a Coke. Well, sorry, a ginger beer. So when we find these, well, this result, it is telling us how many different sequences we could do of the different outcomes. All right, that's it for that first, well, technically second problem. Any question for that second problem?
No.
Cool. All right, so let's do this next problem. So if you're a guy, you probably will relate to this. So it's saying you have 5 shirts, 3 pants, 4 shoes, and 2 belts. And we want to see how many different so it's asking us how many different suit combination can we do. So this is assuming if I change a belt, that's a new suit. So say if I have a black belt and a blue belt, just by changing the belt color, it's telling me this is a completely new suit. So you're saying like if I change something in the suit, it's a new suit for us, okay? So for this one, we could do a shirt. We could do pants. We could do shoes. And we could do belts. All right, so let's do a different color. So for this one, how many shirts do we have to choose from?
Yeah, 5.
You have 5, so you put 5 there. What about pants? How many pants do I have to choose from?
3,
Yeah, 3. What about shoes?
4,
And lastly, belts?
2.
2. So let's see, how many different suit combination can we get just by changing one thing? So we'll say
20, right?
5 times 3 times 4 times 2. Cool.
That's a lot of suits.
And you get 120. So that you're saying like if you pick like a black shirt with black pants with black shoes and black belt, that's one outcome. But if I change something in that suit, now I have a completely different suit.
That's crazy.
So it's saying we have a total of 120 different suits combination that we could do. All right. Any question in regards to that one? Cool. All right, so let's do the last one. So for this one says there are 4 ways from Los Angeles to Dallas. There are 3 ways to Dallas to Green Bay. How many possible ways will John have to get from Los Angeles to Green Bay? So pretty much for this one, they're flying. So to go to LA to Dallas, that's 1 airplane trip. And then they're gonna go from Dallas to Green Bay. And for this one, we're assuming all of the time work, so they're not conflicting. So from LA to Dallas, how many different flights can they choose?
4.
4. All right, what about from Dallas to Green Bay? How many flights can they choose?
3.
3. So if we multiply them, we get 12. So there are 12 different possible flight combination that they could do that would get them from LA all the way to Green Bay. And that's it for that last problem. Any question for the last one? All right, cool. So let me pause it right here for that way it won't be